Okay, in our last class, we were talking about the phase diagram for van der Waals theory, right? And so we worked through this calculation where we figured out the Gibbs free energy for the van der Waals model. And then we can minimize the Gibbs free energy over volume to see what's the optimum volume at each temperature and pressure, right? And so that makes a three-dimensional graph like this one, right? And so we can see that at high pressures and low temperatures, there's this low volume phase, a high density phase. That's the liquid. At low pressures and high temperatures, there's this high volume, low density phase. That's the gas. Right? And then there's a borderline between them where there's a big jump in the density between liquid and gas. And it's a big jump at low temperatures and pressures, but as we move along and follow the boundary up to higher temperatures and pressures, the jump gets smaller. And at some particular point, the jump goes away and the liquid and gas just merge into the same phase. And that point is the critical point. Okay? So it's different from the triple point. It's a different kind of point. And so this is the point. The special thing about it is that's where the distinction between liquid and gas goes away. So if we look at this picture from above, let's see, so that we have pressure on the, oh, what did I do? We want to have pressure on the horizontal axis and temperature on the vertical axis. Whoops, something is going backwards here. Huh. Let me try to reset it. Well, I'll just skip ahead. So if we look at it from above, we can see pressure on the horizontal axis and temperature on the vertical axis. Okay? And here's the boundary. Okay? And so in the 3D plot that I messed up, there's a jump, right? And there's a big jump across the boundary here. And then there's a smaller jump and an even smaller jump. And right here at the critical point, the jump goes to 0. Beyond that, no more jump at all. It's just one phase. This is the phase diagram of a typical material that can form liquid and gas phases as a function of pressure and temperature. Okay, so if you know the pressure and you know the temperature, you could look on this phase diagram and see what phase the material is in, right? And you could see, is it in the gas phase? Excuse me, the gas phase is at high temperatures over here. Is it in the liquid phase at low temperatures over there? Or is it out in this supercritical region? Now the axes on this are in some funny units where the parameters a and b are both equal to 1. But if we have numbers for a and b in SI units or any other system of units, we could do the same calculation and that would just rescale these plots to make real pressure units and real temperature units. Now, the idea of liquids and gases is totally familiar to you, right? You deal with those things every day. Right? The idea of a critical point is not so familiar. Right? We don't normally see the difference between the liquid and gas going away in everyday life. Right? And that's because the critical point usually happens at a pretty high pressure. Okay, so here I looked up some numbers for a couple of materials. Okay, so for water, the critical temperature is at 374 Celsius, and the critical pressure is at 218 times atmospheric pressure. And for carbon dioxide, the critical temperature is 31 Celsius. That's actually not so high, right? But the critical pressure is 73 times atmospheric pressure. So this is not something that occurs in everyday life for us on Earth, but it can certainly occur in the laboratory. People deal with supercritical fluids in the laboratory and in high pressure cells. So this is a real phenomenon. Now, I would say that when you look at a phase diagram like this, the most interesting single point is the critical point, right? That is the weird point where the distinction between liquid and gas goes away. And so what I want to do now is to zoom in on the critical point and see, what can we say about what is the temperature and pressure and volume per molecule at that point? And what happens if you go a little bit away from that point? Okay, so that's what I'm going to talk about today. Okay, so first, let's see if we can just find the critical point algebraically. Okay, so we found it graphically before. Here's the graph that I sort of messed up, okay? And we see there's this boundary and it ends, right? And so we can find it graphically by just adjusting pressure and temperature and then seeing what's the difference in density between gas and liquid, okay? So let's try to zoom in on it. So here, I'll go back to my Gibbs free energy plot. Okay, so suppose, okay, here's a Gibbs free energy plot, okay? And I have these sliders to adjust pressure and temperature, same as we did on Monday. Okay. And then on this plot, we can vary the volume per molecule and see what's the Gibbs free energy. Okay, so for the particular pressure and temperature that I have right up here, we can see that the minimum is here at about 1.8, volume of 1.8 in these funny units. Okay. And now, well, what if I increase the pressure, right? Well, excuse me, what if I decrease the pressure? If I decrease the pressure, that favors the gas phase. So if I decrease the pressure, at this pressure, I have the same Gibbs free energy for liquid and gas. Okay? So this temperature, 0.2622, and this pressure, 0.0223, right? This is on the phase boundary. This is right on the boundary between liquid and gas. And there is a certain difference between liquid and gas, a difference in the volume per molecule from 1.8 to about, 7.8, something like that. Okay, so this is not at the critical point because there's a difference between the densities of gas and liquid. Okay, so now suppose I want to search for the critical point. Well, I think it must be up at a higher temperature than this. So I'll raise the temperature a little. And then I better raise the pressure to stay on the phase boundary. Okay, so now I'm back on the boundary, but the difference between gas between liquid here and gas here is smaller than it was. Okay, I better raise the temperature more. I'll raise the temperature way up here. And I'll raise the pressure here. Okay, now there's still two different phases with equal Gibbs free energies, but the difference is pretty small, right? So I'm getting close to the critical point. Okay, so I'll raise the pressure a little bit more, and I'll raise the temperature a little bit more. Getting closer. Pressure a little more. Raise the temperature a little more. Okay, I'm very close now. These differences in density or volume are very small. Okay, and if I go up, I don't know about there and there. Well, that just about does it. There. Okay, so right about here, the difference in densities between liquid and gas has gone away, right? And we see just a single phase with a minimum, you know, about here, about a volume of 3, right? And so based on this, you know, graphics, I can say here we have approximately identified the critical pressure and the critical temperature and the critical volume also, which is about 3. Okay. Now, suppose instead of doing it graphically, I wanted to do it algebraically. Okay, so I would need equations to represent what I just found by eye, by moving the sliders around. Okay. So I need to solve for 3 things. What's the pressure? What's the temperature? And what's the volume, right? The minimum right there. Okay. So I need 3 equations to solve for these 3 things. Okay. So we could say, well, what should the 3 equations be? Well, when we are finding, you know, when does the graph look like this, right? So we want to find certainly a place where there's a minimum of the function, right? So that means that for sure the first derivative has to be 0. Right? And we don't want the minimum to be a parabola going up or a parabola going down, right? We want it to be a really flat minimum, okay? So we also want the second derivative of the Gibbs free energy to be 0, right? And then we don't want a function like y equals x cubed, right? That goes like this, or right, that's going down in either side, right? So we want the third derivative to be 0 also, okay? So we are getting towards a function that looks like a y equals x to the 4th, right? That has a minimum, but it's a really flat minimum, right? That's what we see graphically here. Okay, so what I need to do algebraically is write out the Gibbs free energy and then find the first derivative, the second derivative, the third derivative, set all 3 of them equal to 0 and solve for the pressure, temperature, and volume. Okay, so let's do that. I'm going to switch now from Mathematica to my iPad to show you how to do that. Let's see here. Okay, so share, share iPad. Whoops, did it work? No, didn't work. Let me try that again. What did I do wrong? Share iPad. Oh, I've got the wrong cable plugged in. Ha, no wonder it doesn't work. Let's try that again. Now it works. Good, good, good. Okay, so here is the Gibbs free energy that we derived earlier. All right, and so now I need the derivatives of this thing. Okay, so we want the derivative with respect to little v. You remember this little v is the volume, total volume divided by the number of molecules, right? So it's the volume per molecule. All right, so the first derivative, all right, that is negative 1 over little v minus b, and then plus a over kt, and the derivative of 1 over v is this negative 1 over v squared. Okay? And then the derivative of this pressure term just gives us pressure over kt. So that's the first derivative. Then the second derivative is like this. So this is positive 1 over v minus b squared, and then negative 2a over kt 1 over v cubed, and the last term has zero derivative. Okay? And then the third derivative. Okay, so this will be negative 2 over v minus b squared, and then positive, oh, I get another factor of 3, so 6a over kt 1 over v to the fourth. Okay, so all three of these things have to be 0. Okay, so we want to solve for pressure and temperature and volume. And wait, this is a 3, 2, right? That's a third power. Okay, so how do I do that, right? Well, I could take, so if I number these equations, right? Number 1, number 2, number 3. If I take equation 2, if I take, equation 2 divided by equation 3. Okay. Equation 2, well, equation 2 says that 1 over v minus b squared is 2a over k t v cubed. And this says that 2 over v minus b cubed is 6a over k t v to the fourth. Okay, so now I will take the red equation 2 divided by equation 3. Okay, so that makes 1 half v minus b is equal to 1/3 v. Yeah, okay. Right. So 3 halves v minus 3 halves b is equal to v, right? 1 half v is 3 halves b. V equals 3b. All right, so that's one of our answers. Okay, so this is the critical volume. So you remember the meaning of the parameter b is the absolute minimum volume per molecule, right? B is the volume excluded by one molecule to the other molecules. Okay, so that's the absolute minimum volume per molecule if you were to put in infinite pressure. Okay, so the critical volume is 3 times that. Right. So there's an answer for that, and then we could combine it with these other equations. So if we want to combine it, let's see if I copy one of them, this one, copy. Okay, so paste. All right, so if I have this equation and I put in what we just found for volume, okay? So the volume, the critical volume is 3B. So this makes V minus B is 2B. So 4B squared is 2A over KT, and this volume is 3B, so 27B cubed. And then what? Then I can solve for temperature. Okay, so KT is 2A over 27B cubed times 4B squared. So K, well, the critical temperature, K times TC, is 8A over 27B cubed. Okay, so that's another result. Okay, and then if we want the pressure, what's the pressure? Well, we could go back to an equation like this one. And copy that. And put it over here. Okay, so now if we put in what we already found for the volume and the temperature at the critical point, let's see, we get then negative 1 over 2B plus A over this thing, 8A over 27B cubed plus P over 8A over 27B cubed is equal to 0. So let's see, if I multiply through by 8A over 27B cubed, let's see, negative 1 over 2B over 27B cubed plus.
Is it B cubed or just over B?
Let's see. Oh, over B. No wonder I'm having trouble. Thank you. Okay. Glad somebody is going to save me here. This is just B, right? That's where I went wrong. 27B. Right. Eraser. A little eraser. No wonder I went wrong. Okay. B. Eraser. Okay. That looks better, doesn't it? Okay. Plus A. What am I doing wrong here? Is there still something wrong? Equals 0. Where did I go wrong? I'm doing it in a different order from in my notes. Okay. Well, I guess I better debug this thing. Okay, if the temperature is 8A over 27B, that matches what's in my notes. Ha ha ha. Okay, good. So this thing is 1 over 2B. Yeah, well, good. Okay. And then A over the temperature. Okay, that looks good, I guess, right? P over the temperature. What am I doing wrong?
That 1 over v squared
Yes,
over in the first at the very top line, the
yes.
second term has 1 over v squared multiplied to it, and I don't think I see that in the second equation.
Thank you. Okay, glad to know some students will save me today. Okay, 1 over v squared. 1 over 9 b squared, right? Because v is 3b. 9 b squared, plus p. Okay, okay, now I'm back to life. Okay, so negative 8a over 54 b squared plus a over 9b squared. 54 is something times 9, right? It's like 6 times 9. Something sort of like that, okay. Plus p equals 0, negative 2a 54b squared plus p equals 0. So p is 2/54. That's 1/27. A. All right, I can do high school algebra. Good. Nice to see it. Okay, so there's our answer. So we have the temperature and pressure and volume at the critical point. That's pretty good. Okay, so now we know these things algebraically. Okay, so if we are in the funny units where A and B are equal to 1, then VC is just 3. And the critical temperature is just 8/27. And the critical pressure is 1/27. Okay, so if you work those out in decimals, those things agree with the results that we had on the graphics. Okay.
I guess at the critical pressure, the fluctuation of the volume would be very large, right?
Yes, excellent point. At the critical pressure, the fluctuations in the volume would be very large. And that's because the Gibbs free energy is not very sensitive to volume there, right? The Gibbs free energy is really flat, right? And so it has a minimum at that critical volume, but it's a very flat minimum. And so the system will have big density fluctuations, big volume fluctuations. That's right. That's one of the features of a critical point. Absolutely, good point. Okay, so now let's see. So this brings us back to the phase diagram. Here, I actually managed to copy and paste the phase diagram here with the notes, with the labels. Okay, good. So that means now we have identified where is the critical point, right? So you can see my marker on top, right? Okay. So that tells us that the critical pressure here is the 1/27, right? And the critical temperature is whatever I worked out, 8/27. In units where A and B are equal to 1, right? Now, if we were working with a real material like water or carbon dioxide, where we have specific numbers for A and B in real units, then we could rescale and draw the pressure and temperature axes in real units, okay? The SI units for pressure and temperature. Okay, so now this tells us where is the critical point, but there is still more information to be had. Okay. What else might we want to know? Okay. One thing we might want to know is what's the phase boundary going out of the critical point, right? We have this boundary, which, you know, it's a line that has some slope right here. Right, and so, you know, presumably we have to do numerical calculations to get the whole line, but there could be some algebraic calculations that would at least give us the slope of the line coming into the critical point. What else could we try to figure out, right? Well, we might want to know how different are the liquid and the gas on the two sides of the phase transition, okay? So on the liquid side, whoops, wrong pen. The liquid has some volume per molecule, V sub L, okay? On the gas side, there's some volume per molecule, V sub G, okay? And we might want to know how different are V sub L and V sub G just on the two sides of this boundary, okay? So how different are the two phases? And we know the difference goes to 0 at the critical point, okay? But so here it's really small, here it's bigger, 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 okay? So we might want to know how that difference depends on where you are, how close you are to the critical point, okay? So that is, we might want to calculate what is Vg minus VL, okay? That is a kind of order parameter here. It's showing how different are the two phases, the gas and the liquid, okay? The same way that the magnetic order parameter in the Ising problem tells us about how different are the spin up and spin down phases, okay? So what can we say about that difference? Well, without calculating anything, we can just look at the plot like this, okay? So this is the plot of volume versus temperature at different pressures. So on this plot, right, we see that the green curve, this curve, right, is right at the critical point. Okay, it's at the critical pressure. So the critical point is right there. Okay, it's that red point. Okay, so the whole green curve is the critical pressure, and then at this red point where there is a vertical slope, that is the critical point. So that is, this whole plot is P, the whole green line is P equals PC. And here, the critical point is at TC, and here's the volume, VC. Now, if we look at a temperature that is smaller, okay? So suppose we looked at this temperature right there, Okay? At that temperature, we know that the gas has this volume, okay? And the liquid has that volume. Okay? So at the temperature, it looks like 0.28, right? Here are the coexisting volumes, the volumes on the two sides of the phase boundary. Okay. What about at this temperature? It looks like 0.245, right? At that temperature, this is the volume of the gas, and this is the volume of the liquid. All right, so I could label it. This is VL at 0.245. This is VL at 0.28, right? This is VG at 0.28. This is VG at 0.245, right? And for one more temperature at 0.22, right, at right along this line, okay, here is, wrong pen, here is VL at the temperature of 0.22. Here is VG at the temperature of 0.22. Okay. Now, this is just at a few specific temperatures, but we could say, now what if I connect the dots to say, what is the maximum volume of the liquid as a function of temperature? I would be connecting the dots to make a plot kind of like that one, okay? And now what about the volume of the gas as a function of temperature? Connect the dots sort of like that, okay? So this we could label as the volume of gas at the phase boundary as a function of temperature. And likewise, this thing is the volume of the liquid at the boundary. So the gas could have a bigger volume than this. The gas, could have a volume anywhere up here. But this is the minimum volume of the gas at as a function of temperature, okay? And then right along this boundary, this is the maximum volume of the liquid as a function of temperature. The liquid could have slightly smaller volume, not much smaller, but slightly smaller. Okay, now, suppose we look at the line, the red line that I just drew. So that is a red line like this one. Okay. In general, it's a sort of complicated shape, right? But now let's zoom in on it, close to the critical point. Okay. If we zoom in close to the critical point, can I actually do that with my iPad? Ooh, I can, cool. If we zoom in close to the critical point, we can see around here, it looks a lot like a parabola on its side, right? When have we ever seen a parabola on its side before, right? Well, in the Ising model, right? We saw something that looked a lot like a parabola on its side. here we're seeing the same kind of thing, right? That this plot for what are the volumes of the liquid and gas at the phase boundary looks like a parabola on its side. Or you could say the difference between the liquid and gas densities is getting smaller as you approach the critical point. And right at the critical point, it goes to 0. So based on looking at a picture like this, we would think, what did I do? Ha, I keep making more pictures like that. Plus, add another page, blank. Okay. Based on looking at a picture like that, right, we can say, what is the trend for the difference of volumes as a function of temperature? Okay, so we want the difference of volumes as a function of temperature. So that is to say, Vg minus VL as a function of temperature. And so it looks like this is a square root, right? It looks like this is something proportional to the square root of Tc minus T. Okay, that's the parabola on its side that I was drawing for you. Or we can write this with the same sort of notation that we used for the Ising model. Okay, so that is, we could say that the difference of volumes is proportional to Tc minus T to the beta power, right, where beta is 1/2. Okay. So beta, this is another example of a critical exponent that says what happens near the critical point. And so van der Waals theory is making the prediction that beta is equal to 1/2. And that's a prediction which doesn't depend on the parameters like A and B. Okay? And so it's just a number, 1/2, right? And so this is telling people that if they go to the lab and they study the densities of liquid and gas close to a critical point, right, that they will find that the difference of densities goes to 0 in this way, right, as a square root, right, as opposed to with some other exponent, right. Now, this 1/2 is the same 1/2 that we got from the theory of the Ising model, right? And in general, this is a result, wrong pen, of doing mean field theory, right? That we have the mean field theory is an approximation, and it is giving us a result of the critical exponent is 1/2. Okay? That's not exactly right. Okay, so if people study it experimentally, they get a different value. It's a smaller exponent. I don't have it in my notes right here. I am remembering that the experimental value in 3 dimensions is 1/8. And so, yeah, mean field theory is not exactly right. But it is providing us with some guidance, right? It is showing us the general structure of the phase diagram. It is showing us that there should be some critical exponent there, but it's not perfect. It doesn't give just the right exponent, okay? But still, we get a lot out of doing this. Okay, now I got this 1/2 by looking at the plot right here and saying this looks like a parabola on its side. What if I wanted to do better than that, right? What if I wanted to do a calculation on the whiteboard, which would actually give us this scaling of beta equals 1/2, okay? So we'll say, you know, how to derive. The general method is using the Taylor series, right? This is the essence of basically all approximations in theoretical physics, right? Is that basically all approximations are based on saying, if you know one point exactly, and you want to know about a point that's near that one. So you make a Taylor series for the functions that you care about. Okay, so here it's a Taylor series about the critical point. Okay, so we figured out what is the critical point exactly. Now we want to know about what happens close to the critical point. So close to the critical point, we will say T is TC plus delta T. And P is PC plus delta P. And V is VC plus delta V. Okay? And now these things we know exactly. And these things we assume are small when we're close to the critical point. And then we work out the Taylor series for the Gibbs free energy. For this Gibbs free energy in terms of delta T, delta P, and delta V. Okay. So this is, it's a straightforward calculation. It's one that has a lot of steps in it, and I think I've embarrassed myself already enough for today, so maybe I won't do that in front of you today, but will instead point you to the textbook, and that is on pages 42 to 44. So please take a look at that Taylor series argument and do ask me questions about it, right? So it's a good thing to do for practice, but it's not a great thing to watch somebody doing in a lecture. And so you should try it for practice and see how that goes for you. Instead of going through all the steps, I'll tell you about one other thing that we can calculate with this sort of method, okay? And so another thing that we can calculate is what's called the isothermal compressibility. So compressibility means if you try to compress a gas, how much does its volume change, right? So if you have a balloon and you apply a pressure, how much of a change of volume do you get, right? Or if you have a water balloon and you apply a pressure, how much of a change of volume do you get? Not so much, right? Okay, and then isothermal means constant temperature. That is, if you're compressing at constant temperature. Okay? So the definition of that thing is kappa sub T is 1 over volume times the derivative of volume with respect to pressure at constant temperature. Okay. And so here we're taking the volume and differentiating it, right? So if you make a little change in pressure, how much of a change of volume do you get? That's that derivative. And then normalized by the volume that you started with. And so it gives you the percentage change in the volume. And the negative sign is because if you apply a pressure, if you increase the pressure, the volume gets smaller. And so this derivative is negative, and then this sign just makes something positive. Okay, so this is a property of liquids or gases, which could be defined anywhere in the phase diagram. But in particular, we can figure this thing out at the critical point, or we can figure it out near the critical point. Okay, so suppose we want to figure it out at a temperature and pressure near the critical point. Okay, in that case, and we'll do it in the supercritical fluid. Okay, so we have the phase diagram like this in terms of temperature and pressure, and here's a boundary, and here's the critical point. And let's say, so that there's no transition, suppose we're at a point, here. Okay, so on the supercritical side. Okay, so that means for the supercritical fluid there at some temperature, delta T above the critical temperature, how big is that compressibility? Okay, and the answer, which is also worked out in that section of the text, is that the isothermal compressibility comes out to be 4b over 3 times Boltzmann's constant times delta T, this delta T. Okay? And so, in other words, when you are very close to the critical point, so delta T is really small, then you get a huge compressibility. Okay? That kind of goes along with the point that Cheng was making, right? That near the critical point, there are big fluctuations. Also, there is a big response to a pressure, right? So when you're near the critical point, even if you just put on a tiny little extra pressure, you get a huge change in the volume. This could be written in this critical exponent notation as T minus Tc to the negative gamma power, where gamma is equal to 1. And so this is another critical exponent relation, that we can derive from this theory. And this also it has an analog in the Ising model for magnetism. It is analogous to the susceptibility of the Ising magnet. And it has the same exponent, right? There was a gamma equals 1 that we derived for the Ising magnet. And in that case, that tells us, if you put a field on the magnet, how much of a change in the magnetic order parameter do you get? And that's analogous here to saying if you put a pressure, an extra pressure on this sample of supercritical fluid, how much of a change of volume do you get? The same kind of result. Okay, so that is my story about zooming in on the critical point in the liquid gas system. So in the next class on Friday, I'm going to talk about what happens if you work at constant volume instead of constant pressure. And then next week, I'll try to get into Landau theory and a more fundamental reason why we have this similarity between the liquid gas system and the Ising magnet.